percent speed regulation or droop characteristics of governors associated with the generator. What we mean by droop characteristics, how that is represented, how that is used in control of generation from the raw material input to a turbine or operation as such. Percentage R, which is represented by the equation which you find on the screen, omega NL minus omega FL to a omega 0 into 100, where omega NL, FL and omega 0 as mentioned there represent steady state speed at no load, steady state speed at full load and nominal or rated speed. In some books, we find N as a representation, RPM directly. So some book refers omega to represent it. Whatever the case, it is a representation of change in speed from no load to full load in the numerator to the rated speed of the generator into 100 to make it into percentage. This we call as speed regulation or a droop connected to a governor of a generator. Together, when I say generator, it means its impact is on governor. Its output is from the generator. Hence, whenever we define speed droop regulation of a generator, it shall mean as a set. It is applicable to a governor, but its reflection is from the generator. Hence, it will be seen in integral to generator only. So therefore, percentage R can be represented as percentage speed or a frequency change to the percentage output change into 100. You can say another representation as a definition. It can be change in frequency as such. Then how you will understand, suppose a generator is having certain X% of droop characteristics or 5% which I have taken as an example here. For example, 5% droop or a regulation means 5% of the scheduled frequency. If I take a deviation, 5% of the frequency which is to be operated as a change in frequency causes 100% change in valve position or output. What do you mean by this? To understand this, let us see a curve plotted. How is this curve plotted? Frequency or speed along the ordinate vertical axis and power output or position of the valve like that on the abscissa or x-axis. Let's say vertical axis and horizontal axis configured as frequency and power output. The plot of response of this particular generator is such a way represented whenever it is at zero speed, mean load on that is zero. What is that? Its speed. Whenever it is fully loaded, what is that? Its speed. Like that, if I connect them, look at the x-axis. Initially it is zero output, then the output of that is ranging to 1 pu or 100% capacity of that. Then when it is no load, nothing is loaded on that, what is that frequency represented by that? It is something a point omega NL. You can see here. The RPM represented to zero output means there is no load on the generator, just it is open. So its RPM is omega NL. Omega NL is the no load speed of the generator. Then as and when generator finds loading on that, load on the generator is gradually increasing. Then I move along the x-axis gradually from no load, load is increasing. Then definitely RPM or frequency, if I make it as an RPM scale, a peak of RPM will fall. If I make this as a frequency scale, frequency drops like that. So when the load increases, definitely my profile which move along this line. So as the load increases, there is a fall in speed. So this will continue to a certain point where when I reach 100% output of that, when I'm drawing fullest capacity possible from that generator, let's say 100 megawatt. When I'm drawing 100 megawatt output from that, what is the frequency it is prevailing to? Then it is called omega NL. It is the RPM at which, or if I say peak of frequency, frequency at full load. So this curve, which is plotted as frequency and power output, show me a tangential like this. Then you will find along the x-axis, y-axis, the frequency or RPM will have its no load value and a full load value. In between these, whatever the point, if I find, I can touch it to a particular tangent line and see to that what is that output I am expecting. It means such curves will be there for each generator. It means to say this curve when I plot, a plot of frequency versus output power, the droop of that generator is expressed as, you can see here, R percent mean delta F bar delta P. It can be delta omega also. It is called deviation. The slope of this curve. The slope of this curve, which is plotted as a frequency and power output, is delta F and delta P. A small slope if I take, that slope represents delta F by delta P as a regulation. So what is this delta F? Delta F is a deviation from a particular point to the next point. So this slope of this curve is what I am speaking as droop characteristics or regulation of a generator. Now let us see something like this. On this particular representation, we just got that no load speed or a frequency corresponds to no load. A full load speed, which is the last end point, which is giving you a fullest output 1 pu or 100% of that at full load speed or full load connected frequency. Then somewhere I have here intermediate between 0.1, 0.2 intermediate. This is omega naught or f naught, called base frequency or scheduled frequency. It is the frequency at which this machine has to perform and deliver the output. Therefore, this is called as operating point of the generator. Certain frequency f naught is defined. Let's say 50 hertz. 50 hertz divided by 50 become 1 per unit. That's something like that. That's called definite set point frequency. That point is intersecting this line. This is a line of a particular generator. Then this 50 hertz are a base frequency f naught or a base RPM omega naught. When you project it to a line, it intersects at this point. Then that point, if I project downward, I will get a value of power what it can give me out being at certain frequency f naught. Suppose if I am running a generator at 50 hertz, then this certain curve of a generator is known to me. On that particular curve pertaining to a 50 hertz of my requirement, what is that output I can see here. This is with the set point only. We have a governor. We are studying these curves because there are two different ways. When I have a generator in parallel, how do they respond for a change in load? Is it the governor only? Is it the set point only? Like that, we have to understand their connected operation. For that requirement, we are trying to understand basically what is a response of a governor for a certain change in load on that. We call it as a droop characteristics. For that to understand, this curve helps us. Then on this curve, important thing is no load speed or a frequency, full load speed or a frequency, set frequency or operating frequency. Then that point we need to understand. From that curve, if I take a slope of that slope represents the regulation of that machine. Then we will come back over here. What is the meaning of 5% droop then? What is the meaning of 5% regulation? It means, you can see here, 5% frequency deviation. Suppose 50 hertz is the frequency. Let's imagine 50 hertz is the operating frequency. For that 5% of operation, 5% of 50 if I take, that's called frequency deviation. Suppose if the load on the generator is increasing, naturally there will be a fall in frequency or a fall in RPM. If I speak about frequency, naturally frequency which is scheduled will definitely to fall when the load increases. Then when a 5% of deviation in frequency, 50 hertz into 5%, 0.05 into 50, that is the working out value I am speaking. If that is the frequency drops, so deviation is noticed, then that is a stimulus signal for the governor to change the input controlling such that it is operating to 100% open the valve. It means 100% opening up of the valve is a signal from this ratio. So this means for every drop in frequency, there should be an opening up of valve to bring it back the frequency to steady state frequency. In what way governor is going to respond for a change in load on that particular unit is defined by its response. Therefore, 5% refers to for every 5% change in frequency, we will be able to control its fullest output in the valve area. So valve opens so that higher inrush of fuel is possible to the governor to the valves to the turbine area and increment in mechanical output and subsequent increment in frequency output electrical is possible. So this means the meaning of droop. So it may be 3%, it may be 4%, it may be 6%, depending upon the machine. So in that respect, the response of these generator for a subsequent load increase will come in the operation. Similarly, when there is a drop in load, suddenly we have to change the set point because otherwise unduly RPM of the generators or a turbine will ride fast. So to reduce it, what is that response concern to the governor as and when there is a drop in RPM, how that is going to supplement. As and when there is a drop in power or load, how that controls the fuel to the turbine so that deceleration is brought out to maintain the normal RPM. For that operation, this value droop is important. In very basic terms, droop nothing but just a particular X% of a generating controller or governor means that X% into operating frequency for which it is working. That hertz or a PU variation, if it is noticed, what the valve will do, open 100%. That is the control possible. When I use this in the numerical, you will be able to understand its impact more clearly. But initially, let us say the basic definition of regulation means it is just deviation RPM from no load to full load to the base RPM, like that. So graphically, a curve which I sketch frequency versus power or RPM versus power, a slope of the curve which I take on this particular representation represent me the droop characteristics. It is delta F by delta P or delta omega by delta P. Then suppose this particular generator, certain generator characteristics I am holding here. If it is operating at 1 PU frequency, I am using the word 1 PU frequency means what? At certain frequency what you have scheduled, that is your base frequency, say 50 or 16 American continent, like that. Base frequency, scheduled it. At that scheduled frequency, what is the output that the generator is developing and throwing out? That is understood from this curve. This curve of that generator and a frequency when it intersects with that curve give you a point of understanding what is the output it is giving. Then further, let us imagine this is 0 output, let's say 50% output, let's say 100% output. Entire length is divided such that the midpoint I am considering is my operating frequency. 50 Hz corresponds to 50% of the generator capacity. So this generator is showing me output of 50% of its capacity at base frequency. Suppose load is increasing of that generator. Load is increasing. When the load increases, it is natural to experience there is a drop in frequency. Definitely, let's say there is no action of governor. Governor is not there. Now I am trying to highlight you the impact or importance of governor, which will regulate the input fuel. If governor is not there, what we would have seen? We would have seen a drop in frequency in meeting the step change in load. Let us see this graphical representation. So this is the point of operation. Let us say load is increasing. Say let's say in this dotted line. This is the line. This point is my next requirement of megawatt. Megawatt originally what it was dealing, megawatt shift is noticed. Delta P is the demand increased on the generator. Then the operating point will shift forward and stop here. Think that there is no governor. Governor is not correcting its input fuel. Naturally, frequency has to be other than the frequency subsynchronous. It is reduced to certain frequency less than f naught or omega naught. Then this is the point of operation. Well, but what is the power output? More than what it was dealing earlier. Let's say P naught, original power, P naught plus delta P is a new value of power it is throwing out. But there is a compromise in frequency. Frequency has come down from f naught to some other value f1. Now the question is this acceptable frequency? Definitely no. If there is no governor action, the prevailing frequency is frequency less than steady state frequency or scheduled frequency. So because of this drop in frequency, there will be an impact on connected loads which are frequency sensitive. Suppose an inductive load XL, 2 pi FL. There is a change in load and there will be an impact of rotating machine. When the frequency changes, induction motors RPM change. Its power draw from the supply keep modifying. That is the reason this is not acceptable. Then what must be done? There is no doubt machine is developing the power and giving you out, because I took a study, let it be supplying 50% of the capacity originally, and there is a shift in load. Let's say small megawatt is loaded extra, frequency has fallen down. Still it has a capacity up to 100% of its fullest length, but in reach of that frequency is compromised. Is it acceptable? Definitely no. Definitely no, because we have seen in the early stages itself, frequency deviations are very much concerned. These deviation will definitely cause distortions, hunting and other adverse detrimental causes to the operation of the power system. Hence, this drop has to be addressed suitably. For that, there is a necessity of governor. That governor will respond to the change in this frequency proportional to its characteristics, so that valves are operated, so that input fuel is supplemented, and this curve, whatever the curve I am shown here, curve is operating, or this point of operation on this curve is at reduced frequency. This point has to be shifted upward. To shift it up, what I should do? This curve I should shift upward. Upward means that point of your new value of operation has to touch the 50 hertz or a base frequency line. Then how it is possible? This curve parallelly I have to elevate upward, shift upward, such that point of operation on that curve touches the 50 hertz line. Then how it is possible? It is possible by governor. Either governor has to open the valve, mechanical input to the turbine increases, output of the electrical power from the generator increases, keeping the frequency constant. What you did here, you have supplemented additional fuel to the turbine. Turbine accelerated, on whose acceleration RPM attained back to the steady state, and your frequency on the load side also naturally became regular frequency. But your actual megawatt output is more than what it was dealing earlier. It may happen. Further, there is a load increase. It may repeat back. Again, it will fall down. Again, governor will adjust it. Likewise, you can go without the governor or with the governor. Without the governor, when I operate this machine, naturally frequency keep falling down and down. It may go to a non-acceptable state even though machine is delivering full load. Or Even though you are at 75% of the capacity of the machine, if there is no governor, we call it as a governor-free action. When there is no governor, naturally frequency is fallen. It may be a subjected issue. Therefore, when it is a governor-based operation, governor's duty is to see to it that such a drop in frequency is worked out immediately and brought to the steady state frequency. That is the reason this group characteristics will play. Any percentage drop of that by X with a frequency deviation, that will make the governor of that generator open the valve from 0 to 100%. Then control it so that the lift shifting is done. We'll see subsequently how it is being done. Now, we are speaking about governor. How exactly governor and generator turbines are viewed? You can just see a block diagram, a valve or a gate input fuel, which is making a representation as an input fuel to the turbine. And this turbine drives the generator. So electromechanical and electrical output. So that we have opposite each other. And this generator generates electricity and drives to the load. Just a single line diagram. This turbine, which is having a governor mechanism, takes the feedback and manage its controlling of fuel, gates or valve such that turbine is regulated such that it develops your required power. This is just a representation. How a governor acts on turbine. So for the governor, feedback is required and output power of that, which is also an important aspect. Then there is an input fuel and there is a correction, and that act on the valve, and valves make the turbine to ensure proper flow of fuel. This is how the simple representation of turbine governor generator is represented. When I have a governor which is shown here, which is acting on the turbine to modify the input fuel to the turbine such that such a steady state of RPM and megawatt is worked out, can be isochronous governor. What do you mean by isochronous? It means you can just see this curve immediately. Isochronous governor, when I say, as a load on the generator, you can just see this graph, which is at the right side, minimum to maximum. Load is increasing, constantly load is increasing. See the frequency or speed of that generator. It is 100%. It is irrespective of the change in load. The governor sets its steady state output. That is called isochronous operation of the governor. It means there should be a mechanism which will regulate the RPM of the particular generator or a turbine to a steady set speed, irrespective whether there is a load of 50%, a load of 0%, or load of 100%. Such an operation we call as isochronous operation. Then where we find this? We find in single generator delivering a local load. For a certain change in load or certain variation in load, that particular governor mechanism sets its RPM or its frequency steady state. Likewise, it is local generation, local operation on individual machines. When I say it is possible, when I have a machines in a station operating in parallel, definitely all the generators are put in parallel to a certain frequency and terminal voltage. If that variation in the frequency sensed by generator 1, sensed by generator 2, generator 3, like that, which are in parallel, they have to act or get acted by their respective governor to change their set points of mechanical input such that steady frequency they will attain again. In that mode of multi-machine parallel operation, isochronous operation is not possible, not helpful. In that regard, it is for only individual generator, individual unit connected to a load, isochronous operation is possible. That's the first meaning of isochronous operation. And isochronous operation means irrespective of the load on the generator, the output or speed is always a constant. Then how this is possible? In the next module, we will see. Before that, let us see how that is represented then. The isochronous mode of governor model block diagram is represented by this way. A turbine. Whatever is the turbine is a turbine. Whatever is the generator, a generator. It is a single line. Then in the lower block, governor, what is inside that isochronous mode? That is the power, again a pickup of RPM from the output, then RPM set, which is omega naught, and omega actual, which is it is running, then comparison of that as an error. That error with the gain, amplify it and integrate over a period mentioned. Then integral controller is taken in the path of feedback, that is making a correction to the steam or water or input fuel. So therefore, an integral controller will always look forward to see to that the average error over a particular observation time span is null and made zero. Therefore, the set point is such a way worked out. Integral of the error which is found in the actual speed and the set speed is addressed as a change in the input fuel to the valve or turbine. In that regard, continuous monitoring is done and integral of the error is corrected at the valve displacement. This valve displacement will make a mechanical supplement to the turbine. Turbine always try to regulate its RPM as expected. Any load change, naturally, when I say there is a load change, it is natural to experience a dip in RPM, nothing but frequency fall. That is again compared with the set frequency or set RPM, immediately that error is integral of that error make the displacement of the valve and valve on whose action input to the turbine is again managed. This way, this is put in practice by isochronous mode of operation. So therefore, it is how an isochronous mode of operation make the steady RPM or frequency irrespective of the load is possible. This is how one representation. The another representation is speed regulation by droop. So we have begun our interaction. What is the percentage speed regulation or a droop, which is given below. The value of R determines steady state speed versus load characteristics of a generator as shown in the diagram. It means percentage regulation we defined as change in load from no load to full load to the nominal or base speed into 100. This is because as and when there is a fall in RPM, fall in speed, definitely this governor will increment input fuel to the turbine and turbine accelerate and set up supplement mechanical input, and that will reflect as change in electrical output as well as frequency shiftment. Therefore, in what proportion this change is getting applied, that is what we are defining the ratio R, the regulation characteristics. It means you may ask me why it is called a droop characteristics then. The droop characteristics is just because there is a natural phenomena as and when there is a load increase on the generator, frequency do fall. As and when fall of frequency is noticed, we call falling. There could be a controlling action on the controller such that will adjust the input point so that the error is brought back to zero. This is how the fall of frequency or RPM is taken as an input stimuli for the controller to shift it back to steady state RPM or frequency. In that regard, the nature of the particular generator or governor along with the generator for a subsequent change in load is noticed. You may ask me, is there anything other way? Will there be a mechanism on the rise of load, frequency also change or RPM change? Suppose imagine there was a mechanism on a subsequent rise of load, frequency or RPM increases. See that for a change of load, first task of the generator is to develop and deliver. While develop and deliver, RPM also by chance, opposite concept I am trying to convey you, shifts forward and above. It may catch over a time dangerously very high speed called as a fly away speed. So all the rotating mass experience fly away and disaster. So opposite not there. Droop is advisable. Droop characteristics are advisable for a control mechanics concerned to hydro or other part of the controlling. Therefore, it is easy when I have a drop in RPM or drop in frequency for a subsequent load on the generator, it is easy to correct on a fall. Then increase of load, even RPM also shoot upward. What is that you are going to correct? Input fuel already sufficient, which is causing more than your frequency or RPM. And how would you address it? That control is not at all good and not at all there. In that due regard, a droop characteristic is a favorable control for generator governors. Hence, droops are always spoken with the generator. That is the history connected to why the droop only. Droop of real generator we will see in the next module, surely. But basically, let us understand why this kind of expectation is there. It is because on whose fall of RPM or frequency, that error is fed into the controller try to open the valve. That's what we are saying. R percent droop means 100% its input valves are opened. It can act 0 to 100% of the opening up of valve for the mechanical supplement. That is how it is very easier. So therefore, speed regulation or droop is very useful in controlling the RPM or input mechanical supplement to the turbine on a fall of RPM or an increase of load in the generating area. So that is given by R equal to delta F by P. This delta F is called frequency deviation. How do you calculate this? Let us look into this curve as usual earlier. This is a curve plot of frequency versus power. Frequency need not be F, it can be omega also. Omega or frequency power. Let's say certain R percent is a drawn line, and at omega naught, this is delivering a certain output, say P naught. Suddenly load on that generator is increased. That operating point which I am pointing with the mouse cursor is shifted to next point. Subsequent to this, frequency is not F naught, frequency is below F naught. That I want to see. Then you want to arrest this drop of frequency and you want to bring this back to F naught. Then what is that? Increment in mechanical supplement, or what is that? Correction in the valves to be done by the governor to make this error back to 0. That is to be known as deviation in the frequency. That frequency deviation can be calculated as difference in omega or F from this way. You can see here F minus F naught. What is the frequency it is prevailing right now on whose incremental load? What was originally F naught? F minus F naught give you deviation. That is the drop in frequency from original operating point, and shift of power or load drop the frequency, and this change is known as frequency deviation. And this deviation in frequency is due to shift in load, that is delta P. A small demand increase is called delta P. Then the slope of this curve can be easily plotted as delta F over delta P. A small slope, delta F, delta P, if I take, that becomes regulation of this particular curve. In that proportion, it is going to work. No other way you just see. So for a particular delta P, you take this delta P to the LHS and bring the R downward. So for delta P requirement, what is that? The particular P it can apply. So this can be taken from this calculation. We will see when I apply to numerical problem, mostly you will be able to realize impact of R on the calculation. So droop kind of calculation works as R equal to delta F by P, where delta F is a drop in frequency. We calculate as F minus F naught like that. Then here also P naught and P1. What is delta P? Shift in load. It may occur other way also. Load is decreased means it will go reverse. Everything go reverse. So this is how droop characteristics can be viewed. This is droop mode of operation of governor. I was speaking about isochronous operation. Here, as and when there is a fall, this governor is going to act on a controlling point. But here there is no constant. It is maintaining the speed irrespective of the load. This is called isochronous. This is droop based. As and when there is a requirement of shift of RPM or frequency, governor will be action. Else, governor is steady. Governor is not correcting anything. It is called steady state. Steady state operation of governor means what? Governor has set a point and kept quiet, and machine is operating. On whose notice of a drop of frequency, governor will again act, correct it, and keep quiet for the next observation. Like that, governor based operation, which is by droop, fall in frequency or RPM for a subsequent change in load, that will correct your operating point to the requirement. Next, how this will happen when we have number of generator acting in a station sharing the load. So this is called load sharing by different units in a plant. Imagine in a station there are 2 to 4 generators, all are running, and we have purchased a machine 1 and 2 from some continent, machine 3 and 4 from our own Indian, and we are putting all 4 together in parallel, and their characteristics like a regulation characteristics are different. They need not be same. 4%, 4%, 5%, like that. They can be any percent R. In that regard, the situation comes. The generator in a station may have same capacity, same characteristics. R is same for them. Output megawatt is also same for them. Ideal thinking. It need not be same. R may be same. Capacities may be different. Machine 1 is 100 megawatt. Machine 2 may be 150 megawatt. Machine 3 may be 200 megawatt, like that. Output capacities may be different, but droops may be same or need not be same. Whatever is that, it comes an issue with operation. Whatever the generator we have, respective to their capacity and their droop, they are functioning and developing output for our requirement. We are truly concerned to our generation aspect only now. We are not looking forward who is doing it. We are just operating. What is the current operating point? What is the shift in operating point if load occurs? How to correct it back is our interaction. For that, load sharing is an thinking. So for this, what I am taken example from the textbook is, let there be 2 units. Unit 1, Unit 2. Unit 1 has its droop characteristics as plot of frequency versus output power. Certain X% droop. Another generator I have in the same plant whose droop characteristics are Y%, frequency versus output. We don't know. Definitely X and Y are different. By V only we can say slope of this curve are not the same, different. Let it be different, not an issue. For me, what is interesting is, let us imagine the 0 output power from this point and 100% output of this edge of this point line, and again 0 output of this second unit to the 100% output of that generator. That line end point you observe, 0 output, fullest output, 0 output, next whole capacity output. These 2 machines are put in parallel. How they share load being in parallel? How they respond for the sudden change in demand in the station? Who will take major portion? Who will take smaller portion? This becomes an issue to understand scientifically. For that, we have taken 2 units having certain droop, certain operating frequency, let us say F0. They are operating initially at base frequency F0. Then I will project the line to both the curves. Can see here. So they are plotted side by side such that they are maintained such that F0 is the base frequency like a 50 Hertz. It is developing a certain power, minimum power and highest power. So it is throwing me some, say 25% of its capacity is taken here. Then let's say 40% or 35% of its capacity is taken out and dealing P2 megawatt. And this is dealing P1 megawatt. Right now for me, at base frequency F0, when I project this line, it intersects with both the lines. With the line 1 of machine 1, P1 is the output, megawatt and P2 is the output of second megawatt. P1 plus P2 if I add, that becomes total power delivered by these two units in parallel. That's what is the basic concept at F0. Let us imagine this situation continues. The governor of this machine 1, governor of machine 2 respond as per the group characteristics of machine 1, machine 2 individual to them. They are going to control their input fuel. Let us say hour plus 2 hour, 3 hour like that. Load is not at all changed. They are developing a power P1 megawatt, P2 megawatt together dealing a load PD or PL load. After certain hour of observation, let us imagine load is increasing on this station and these two generators are said to be in parallel. Then how they will respond? That's what is called as, let us assume there is a delta PL increase in the load. Delta PL increase in the load, this will cause governors to respond. Suppose say RPM will definitely fall down if there is an increase of delta PL or a load on the parallel connected generator. Let us say due to the change in load, say frequency has fallen down. Let's say frequency has fallen down and delta P1 plus delta P2 be equal to delta PL. What I am trying to convey you is the shift in demand, say 10 megawatt. Let 10 megawatt is the load additionally demanded. P1 plus P2 were dealing your requirement. Steady state was there. Suddenly 10 megawatt is extra demanded. How this 10 megawatt is addressed by these two generators, I am trying to convey. Let us say this 10 megawatt is equal to delta P1 plus delta P2. Delta P1 plus delta P2 together become shift in demand. Then what is the portion of the 10 megawatt or delta PL is taken by machine 1? What is the delta PL's portion is taken by machine 2? We are trying to work it out. To work it out, let us say this delta PL being a net change, then this will cause frequency to fall down. Let us say on whose falling, let's say F is the frequency or F dash is the frequency. This frequency will be again having a line projected forward. If I project a line here, that will intersect with this first unit's value and second unit's value. Then what I will do, these two width, vertical width between P1 and some other point P1 dash, I call it as expected change from machine 1, expected change from machine 2. If I add these two, it must be equal to PL. And what is the frequency if the governors are not there? It is F dash. Frequency has naturally fallen down. That reduced frequency made the operating point of this on the line which is P1 dash. On this line it made as P2 dash. Then what is P1 dash? What is P2 dash? Definitely P1 dash is the new set point. P2 dash is the new set point on machine 2. Then how it is calculated? That is called from the original P1, this shiftment is demanded. Delta P1 is demanded on the generator 1 so that delta P1 plus P1 become P1 dash. Similarly, on the machine number 2, P2 was your operating point. Megawatt what it was developing earlier was P2. Suddenly a shift of demand delta PL raise the value of this P2 as a delta P2. P2 plus delta P2 become P2 dash. Then what is that share of delta P1? Share delta P2 on whose notice I can calculate P1 dash, P2 dash. How it is being done? Look into this. Delta P1. This delta P1 is from the graphical way when I have this frequency line intersecting with this curve at certain point at the reduced frequency made me to read P1 dash. P1 dash minus P1. P1 dash minus P1, nothing but shiftment required. Delta P. That's what it is. Delta P1, the share taken by the generator 1 is P1 dash minus P1 is delta P1. Similarly, P2 dash minus P2 is delta P2. If I add them, delta P1 plus delta P2, what it should address me? It should address me delta PL, net load shift. So this is how this delta P1, delta P2 are the corrections required at machine 1, machine 2 respectively to meet your requirement delta PL. Then how the governors in the rear work or rear side do this correction? They do this correction by this way. So this change in power is delta F by R1. Then I go back and tell you what is droop characteristics. Droop characteristics of a certain generator is delta F by delta P of that machine. Delta F by delta P. Using this, if droop is known to you, what is delta P required? I can calculate delta P equal to delta F divided by R. That's what I am doing here. Delta P1 is the shiftment expected from generator 1 viewpoint for the change in load. That is P1 dash minus P1 is delta P1, which must be correction to be taken from governor mechanism of machine 1 as delta F by R1. R1 is the droop characteristics of machine number 1. Similarly, delta P2 is P2 dash minus P2, which is equal to delta F by R2. Why you took delta F same? Because these two machines are swinging hand in hand. The deviation what is noticed here is the same noticed deviation here. Therefore, delta F by R1 is the expected shift in correction of a supplement of power in the machine 1, and delta F by R2 is the corrected shift in the supplement of power in the generator area 2 or unit number 2. On whose ratio, if I take delta P1 divided by delta P2, if I take this equation on equation 2, delta P1 divided by delta P2 equal to this equation, delta F by R1 whole divided by delta F by R2. Delta F cancels, the ratio remains R2 by R1. You can see here. The proportionate shift delta P1 is R2 by R1 into delta P2. If I write this delta P2 in terms of load, I can definitely write what is delta P2? Delta PL minus delta PL1. If I express this, delta PL is what? Delta P1 plus delta P2. I can definitely do. So therefore, the proportionate pickup, you can see here. Delta P1 is here, R1 is at the denominator. Delta P2 is here, R2 in the numerator. What do you feel by this? Inverse proportion to their characteristics. Delta P1, delta P2 are the corrections required over here are inversely proportional to their characteristics. This is the ratio I understand. Now, if I have a machine, the machine with the bigger capacity surely share highest capacity as well. Machine with the droop, you can see here, the droop curve, the value of R1, R2, which is sharing. So this machine R2 or machine 2 with the R2 value is sharing higher megawatt. Machine with the R1 is not sharing higher, sharing less than this. So in this way, the share of power or share of disturbance, share of load is done in proportion to their characteristics we speak about. That is inversely proportional to their characteristics. There is a change in capacity. So therefore, the inverse proportion of their regulation cause set point change on the governor to respond for the load. You can see here, if the percentage regulation of the units are equal, suppose say R1, R2 are equal, both the lines are parallel to each other. Droop of R1, droop R2 are parallel to each other. It's called percentage regulations of units are equal. The changes in the outputs will be nearly equal. Delta P1 is nearly equal to delta P2. They share equal to their total load. Delta P1 plus delta P2 equal to delta PL, no doubt. But individually, both will be equal in share. But now, they are not in equal because droops are different. In that respect, the share of disturbance, share of load from the generator perspective is in proportion to their characteristics involved. So therefore, because of this droop characteristics, increase in output is accomplished by steady state change in frequency deviation. So this proportion to that, there will be a change in input field. Automatically these lines are brought back to F0. When you go to the next chapter, surely we'll be having how this frequency F dash, which is fallen down, is addressed back to base frequency. Again, what is that calculation we will doing? So presently, let us say how that sharing is done. To shift it back, governor has to act upon. How sharing takes place among the generator is by this way, proportion to their characteristics like that. Suppose you will see all comparison in a single sheet. When I say isochronous, it is the first curve in the left side. Irrespective of the load change, it is constant RPM or a constant power. If it is loop based operation, let's see this curve. There is a no load speed or a no load frequency, full load speed or a full load frequency, and steady speed of operation or steady frequency. And output curve at this point is say some power it is showing. For this curve, say 50% of the output is seen at steady state frequency. And the load increases to full capacity, 100% loading. I cannot develop 100% load here because frequency falls down. When I want to develop or load more and more, frequency naturally falls. Without the governor operation, if I want to operate, I have to compromise the drop in frequency. Therefore, that is not acceptable. To have it operated at full capacity and at base frequency, this curve has to be shifted upward. To shift it up means mechanical input has to be provided to the generator turbine combination. How it is being done? That is to see how governor based operation is important. So from this first curve, basic droop we understand R is delta F by delta P, or delta F is deviation in frequency from actual frequency right now and base frequency what it was. Now, when I see this droop operation, output obtained here is say 50% at base frequency omega naught or F naught. If I increase the load, naturally frequency is less than the base frequency. Now, if I want to make governor based operation, see this curve here. This third curve show you parallel curves represented. Let us say a speed droop curve with change in governor set point. Governor keep modulating the output of the valve. How is that? Let us take a horizontal line F0, a base frequency. At that point, it is called nominal speed at NL. Then power output is something else here. Then suppose that is called no load output. Then 50% of that output you want to encash. Then you have to increase the valve, open the valve such that R% based control. Then definitely this line is shifted forward. The mechanical input, if you supply more and more, when the load is increasing, as the load from the no load 50% you want to increase, at 50% of the output from that generator, it is operating at base frequency. This is the operating curve of that. Suppose load of that you want to make 100% delivery. On this curve, let's say only on this curve, if you increase the load without the governor, what will happen? It will come to a line where 100% power delivered at reduced frequency below the F0. So it is not acceptable. Then what should be done? So there should be a nominal output 100%. Then mechanical supplement to the turbine has to be there such that base frequency is also F0. Then this curve, no load and 50% load and 100% load, these curves are parallel to each other, shifted upward at a droop nature. There is a correction in the governor mechanism to supplement input to that such that no power output, 50% output at base frequency and 100% output at base frequency. This is called as governor is monitoring and controlling such that frequency is also kept constant. Error is managed to zero and output is also managed properly from its no load to full load. This curve shows the steady comparative. When it is a no load curve is shown in this way. This curve. Only on the no load, base frequency is noticed. As the load increases, frequency falls back. It is not acceptable. Then the shipment is brought. For obtaining 50% of that generator output, mechanical supplement has to be done, then it is falling somewhere here at the 50%. Further load is increasing, frequency has to improve again. Then you have to implement the control such that line is shifted upward and you are bringing 100% point coincide with the 50 hertz. Then you are making 100% output. So from this line, no load, 50% load, 100% load, shipment is done by the governor's set point change that is being done. Suppose if you see another curve similar to that, you can just see just a line, a blue line you can just observe. Load reference for nominal speed, no load. There is no load, just this is a line, blue line. And suppose load reference point for 50%. When there is a 50% load on this, I cannot leave this no load curve. I have to see to that input to that turbine is managed, that line is shifted where the line 50% value of that coincide with the base frequency required. Frequency line has to intersect this operating curve, which is 50% by its value. Then this is said as developing 50% output at 1 pu frequency or your desired frequency. Further, on this line only I need not keep operating without correcting the governor. If I increase the load will ride forward, but frequency will be noticed different. Then to obtain 100% output of that with the base frequency constant, then this line has to be shifted forward. Again, input increment has to happen. This is what this curve says. Droop curves keep correcting. The subsequent drop of frequency or RPM is corrected by relevant opening up of valves at the controller, so that mechanical input will shift the RPM and frequency back to requirement. So these governor free, this is the isochronous operation and droop mode operation, in which governor free with governor operation we can distinguish. Governor free means governor will not be there. Whatever is the line you have, only along the line it keeps operating. Suppose this line, central line, if I assume governor free means it operates fullest capacity, its output and drops continuously. There is no correction required. If there is a governor will act along with the requirement of a steady state frequency achievement. Correction to the input fail is done. So this is how isochronous and droop mode based operation is possible. Further, if I just see the similar curve I have extended, a simple curve from one generator perspective. How it is being written? It is written by plot of frequency versus output. Why I am showing you? Because on this only you have lot of numerical problems to be worked out, and there could be a short derivation show that load sharing among the generator takes place in proportion to their characteristics and capacity. Then how is that? To show that these curves will help you to understand. So let us say single machine curve, a plot of frequency versus power. Certain droop is noticed. For certain 1 pu output, fullest capacity output, frequency is say F0. It is configured. If the load is decreasing, let's say frequency shoots up. So governor has to again bring this line down, close the valve. If it was said at some other point, it may have happened other way also. So it is base frequency expectation, output of fullest capacity is operating. Further load increase, it may not be possible from this. So this is how F0 and base output is shown to you. Then when you have such two generators sharing parallel, curve 1 machine 1, curve 2 machine 2. So droops are different, and here also I have shown droops are different. R ratio, R value is different here. Definitely initial value of operation is P1 point with a load P1, and it is operating at output P2. P1 plus P2 were meeting your demand, and suddenly F0 was your frequency. Load increase is noticed. Say delta PL. If delta PL is delta P1 plus delta P2 suddenly, then what is delta P1? This is the shift. What is delta P2? This is the shift that is shown here. So this curve, delta P1, delta P2, original power set point, original power set point, revised power set point, revised power set point, P1 dash, P2 dash, like that. So what is that delta P1 then? Shift in demand. Shift in demand is new set point minus the old set point. That is called delta P1. Expected change in the machine number 1 area, which is equal to, on the droop nature, it is called deviation frequency divided by R1. Similarly, deviation in frequency divided by R2. If I take a ratio, delta P1 by delta P2 is again R2 by R1. The same thing I wrote once again. Delta P1 equal to delta F by R1, delta P2 equal to delta F by R2, ratio when I take this. The same thing in some books they refer on a single graph, left side, right side they mention. Left side one generator, right side another generator. Same curve. The bluish by curve, reddish by another generator. What is being done? Let's say vertical axis is frequency. This is frequency, what they are commonly working upon. Left side is one axis of generator 1, right side is another drawing for generator 2. Let's say a blue line which is plotted, red which is plotted, intersecting with the horizontal line. You can just see this line I am trying to show with the mouse cursor initially. This is the point of operation, certain F frequency intersecting this line, developing Pg1 output. And the same point when it intersects with the red line, developing Pg2. I mean Pg1 plus Pg2 equal to Pg or P load. Load is being addressed as a share from machine 1 as Pg1 megawatt, like our P1, and share of machine 2 is Pg2, like our P2. Pg1 plus Pg2 equal to P load at frequency F. Suddenly, load is increased. What will be an observation? A drop of frequency. A drop of frequency, suppose a line, just one line below, you draw a parallel line here. A line parallel, like this. A line parallel will intersect with the first curve, different point, second curve at different point. There will be a change in power output from machine 1, change in power output from machine 2. That output I have to calculate like this. So this is how a common diagram for machine 1, machine 2 is also used to present. But here what we have done, two separate curves we have drawn. You are drawing a horizontal line to intersect here to get our understanding. So this way or this way, whenever you find, it is called load sharing between parallel units. So this would be the outcome of that. So if I see how that will be going to come in picture, whatever the governor I am speaking, this is the governor, if you imagine, speed governor, which is acting to the control of fuel, hydraulic actuator, speed feedback and fly ball mechanism, speed set point, then your pilot valve and main piston and main operating point. If I connect these things, whatever the governor I am speaking, if I connect these things, how this valve opening, closing is done. So for that we have the output of the governor, this particular governor which is rotating continuously by fly ball mechanism. This is going to change the displacement of this particular point A, B, C, D, E. These are the power displacement I was picking. Whatever the set point you have done, how that set point will be making this governor to open and close for a change in RPM or change in load. As the load on the generator is increasing, what is my observation? This RPM of this feedback will lower. This will reduce. If the RPM falls down, then it has to open the valve so that more fuel will go. So this way, what is that it has to open? How much it has to open is the relationship of governing mechanism by droop nature. So therefore, these connections, these understandings of opening of all, closing of all from the feedback network and set point network and hydraulic actuator mechanism can be connected to one another. This will be done in next chapter. Meanwhile, I am just trying to show you that whatever the feedback speed which is fallen down is going to get reflected over here. This will shift the set point such that that can shift from this feedback which is lowering down or raising upward will make the valve close or open in proportion to their characteristics. That is represented by this way. The change in output of the governor is possible by reference point. I can change the controlling of this valve directly by this way. That's called reference point changing. The other is the speed of the governor can change. So why I am showing this means here repeatedly I am speaking. When there is a load increase, definitely frequency or RPM falls. Then this RPM fallen has to be corrected such that governor operates the valve and valves open the input fuel and shipment in the frequency or RPM brought back. That's what I am trying to connect. This is the governor's feedback. Means governor which is connected to a speed will keep on rotating. This rotating governor flyball mechanism reduce the RPM itself when there is a load increase. Because shaft reduces the RPM, this also reduces. Once there is reduction, this point will be lower down. This will be pulled down. So not pulled down, it will be raised up, because when there is a whirl effect, when I have a stone and thread rotating around, definitely it comes down. It comes down means vertically it elongates. These 2 points vertically elongate whenever there is a reduction in speed, and these 2 will come down horizontally elongate when there is a high speed. So this way I can change the valve open close condition depending upon the speed feedback of the actual turbine, which will be reflecting on the particular valve. Or directly I can modify, increase or decrease. By having it acted manually, I can reflect this change directly to the valve open close display. That's what I am speaking. Governor free, governor based operation. When I was using, when governor is not there, this is null. There is no action of this. How can I change the input fuel to the turbine? I can change set point. Set point is changed. Its impact is on open or close. Direct 1-to-1. Increase, increase. Decrease, decrease. That's all. Suppose according to the fall or rise of RPM due to load changes, you want to work. So that time you are using this feedback method. That's what I'm speaking. Change in reference point is the one mechanism to increase or decrease the fuel input. Otherwise, change in speed of the generator, that is frequency, and that will be reflected by this governor feedback to reflect it at the other side. Whatever the droop I am speaking concerned to this area. So this will respond in proportion to the characteristics mentioned. Then it is like this way. The governor's output of this, what is that correction it is going to apply over here is given by delta PG. Delta PG is what is being set here, P reference minus what is the deviation in frequency? Frequency delta F by R. Delta F by R. What is delta F by R? If I go back, what is delta F by R? Delta P. Nothing but mismatch or change in demand is nothing but delta F by R. In general terms, what is delta F? You can just see here. Delta F by R is delta P. Delta P is called net change demanded. Net disturbance, net change in load is delta F by R. That's what I am trying to connect here. So delta F by R is the power, demanded power, actual reference power. Mismatch is nothing but correction given by this. So how mechanically and mathematically connected now here? The power which is really required depends on the actual RPM. If there is a drop in RPM, what you should be doing will be opening the valve to increase the RPM. That is reflected by this rotating mechanism. So output of this governor mechanism is on the reference point. If the reference point is able to meet the requirement, there is no correction by this. If the reference point is not meeting the requirement, then correction is applied by this. That's called P reference minus delta F by R. This is called shift. This is done. So this is used in our calculation. So I am speaking about how this governor come into picture. So we'll see this in the next chapter carefully once again. So there are two cases to see. The change in turbine power, PT, mechanical input to the turbine, and change in the generator output, PG. The PG is nothing but whatever is the power developed by the generator to meet your balance. That balance shortfall is nothing but the acceleration of generator turbine. That's what is called change in turbine power is nothing but change in generator requirement. So The accelerating power is said as mismatch between these two. Delta PT is the shift in turbine input is nothing but demand in generator output. So both have to be addressed. So accelerating power in frequency domain, we Laplace transform when I want to apply delta PT minus delta PG stand as accelerating power. On this accelerating power, I have a statement. If delta PT minus delta PG is negative, what do you mean by this? Delta PT minus delta PG, demand from generating side, demand from turbine side, means increment applied by the turbine, increment required by the generator. This value is negative. It will decelerate. It will reduce the RPM. Then turbine power increment, delta PT, what is to be applied to the turbine power, whether to increase the mechanical input or reduce the mechanical input to the generator, is depends on delta PT, depends entirely upon valve power increment. See here, valve means the valve which are really opening the input field to the turbine. We call them as a displacement. Valve output. So incremental change in valve position, nothing but incremental change in turbine power. So that is again given by first order lag function in the transfer function of the activity. So this also we will see in the next chapter very carefully. For me, just to say how that mechanical input supplement your electrical requirement, I am trying to connect it. This is the subject of your next chapter only. But for me to connect you, how this turbine, which the valve open close concern to your generation and your set point and governor, I am trying to correlate it. Required change in input mechanical is nothing but demand change. That is done by two way, one by set point change or by droop mode of control. That I am trying to connect to you. So turbine power shiftment depends on your valve requirement. Valve requirement again depends entirely on your generator's requirement. If there is a demand, there is a generator to generate more. If the generator to generate more, turbine power has to be more and more. Like that, there is a reverse connectivity from one to one, one to one. So therefore, one simple thing I can just correlate. A generator is assumed to be synchronized to a network of a very large size. It's a infinite. So that the frequency will be essentially independent of any change. If the output of individual generator connected to infinite network, since delta F is 0, deviation is 0, it becomes whatever the reference you set is a turbine. It means if the generator is assumed to be 10 megawatt, there is no frequency deviation at all. It is infinite in energy. Therefore, whatever the change in power you apply, change in mechanical input. So there is no droop required here. It means infinite network you are connecting, it is able to make your requirement. There it is a statement called as a generator operating at constant speed. There exists a direct proportionality between reference power setting and turbine power. There is no droop into here. How it is understood? Take a simple example. A 100 megawatt 50 hertz generator is connected to an infinite network. How would you increase its turbine power by 5 megawatt? It means 100 megawatt generator at 50 hertz operating point is working. Let us imagine working at 50 megawatt output. It is developing 50 megawatt at 50 hertz connected to a network delivering the power. There became a necessity. 55 megawatt is the demand. Megawatt 50 become 55 over time. How would you change that 50 megawatt to 55 megawatt is the question here. That is a situation when the infinite network is connected to a generator or a generator connected to infinite network, droops will not come in picture. That is what I am trying to say by case study. Whatever the droop we have discussed, R% like that, when infinite network is considered, the droop will not be in picture. Whatever the direct proportion, 5 megawatt you want to change only 5 megawatt turbine power. That's called turbine power be increased by 5 megawatt, simply giving rise command. It means I go back and show you. So there is no turbine operation, governor operation. Governor is null. Increment of 5 megawatt means increment of 5 megawatt command here only. You command here, it will act here. You decrease, there is a decrement command, decrease this. It means governor free operation. When the generator is connected to infinite bus, infinite network, this is a change. So 5 megawatt mechanical input,